Swayam Prabha. Digital India. Educated India.
So, applying Kakutani's fixed point theorem, we are going to get to Nash's theorem. So, this is Nash 1. There exists a y1 star to yn star such that ji of y1 star to yn star is less than equal to ji of yi comma y minus I star for all yi in capital Yi and for all I in n. This is what we are going to prove. Okay. So, the proof idea is going to be to simply apply Kakutani to R. Okay. So, what did we had just established that Y is a Nash equilibrium if and only if Y star is a Nash equilibrium if and only if Y star belongs to R of Y star. That means, if and only if Y star is a fixed point of R. So, to show that there is at least one Nash equilibrium, all I need to do is show that R has a fixed point. Okay. So, and now to show that how will we show that R has a fixed point? We will show that we will apply Kakutani's fixed point theorem, which means that we are going to show that if I take phi as R, all these hypotheses are satisfied. Okay. So, that's going to be the proof idea. So, we need to check a few things. So, let us go through them one by one. So, in order to apply Kakutani's fixed point theorem to R, we need to check that the domain of R is closed, convex and bounded. We need to check that R actually maps that set, the domain, to subsets of itself. We need to check that R is convex valued, and we need to check that R has a closed graph. Once these are checked, Kakutani will then give us that there is always a fixed point and hence there is always a Nash equilibrium. Okay. Alright. So, firstly, what is the domain of R? So, domain of R, remember, was is Y. So, R maps Y to subsets of itself, and so R is in fact a mapping from a set to subsets of itself. But is this domain closed, convex and bounded? So, what was Y? Remember, Y was simply the product of these yi's, right? Y was the product of these yi's. Each yi itself was a set of probability distributions on a finite set. So, probability distribution, that means basically it's every component is between 0 and 1. So, the each yi is basically in some box of dimension 1, lying in some box of dimension 1 in its own space. So, y being a product of all of that is in a hyperbox of higher dimensions, but at the end of the day it is in some box in some bounded set in its space, right. So, therefore, since yi is the set of probability distributions, the set of probability distributions on SI. This is in fact, so this set is therefore, yi therefore is bounded. It is also closed because you take a sequence of probability distributions, it will converge to and if it converges, the limit will also be a probability distribution. Why? Because you can see that if I take vectors yi say yi k, these belong to y, capital Yi, and if I take their limit as k tends to infinity, take the limit of k as k tends to infinity as yi, suppose they converge to some yi, then each of these belonging to yi means that this equals 1 for all k. It also means that this is greater than equal to 0 for all k, and therefore, if I take the limit as k tends to infinity, the limit should also have this property that 1 transpose that limit would be equal to 1 and that limit would be greater than equal to 0, which effectively implies that 1 transpose yi will be 1 and yi will also be greater than equal to 0. So, in other words, therefore, yi is bounded because these are probability distributions, and it is closed for the same reason. And then what about convexity? You take two probability distributions and take a convex combination of those two probability distributions, that is another probability distribution, right. You mix two probability distributions, you get another probability distribution. So, which means that it's convex. Another way of looking at this is that, remember, capital Yi is simply defined by linear equations and inequalities, okay. So, therefore, it is a convex set and it is also therefore a closed set, okay. But because these the distribution, what it defines is a probability, is the set of all probability distributions, it automatically is bounded as well, okay. So, in other words, capital Yi is closed, convex and bounded, okay, alright. So, once capital Y is closed, convex and bounded, therefore, Y is also, being a product of such sets, is closed, convex and bounded. So, with this, then what we have ticked off is this. We have ticked off the first part. So, this one, we have a function that maps a set to subsets of itself, and it's a domain to subsets of that domain, and that domain is a closed, convex and bounded set, okay, alright. So, the first, this is done. Now, let us go to the next one. So, now we are looking at this one. We need to ask, is the function, is their set valued map convex valued, okay. That means, what we are asking is R convex valued, okay.
How did we show
Convexity,
convexity?
I just said that it follows because you take convex combination of two distributions, it's a convex, it's a probability distribution, okay. Alternatively, you can see that Y here, you see Yi is just defined by linear inequalities and equations. So, therefore, necessarily Yi is a convex set, okay, alright, okay. So, now we will be showing that R is we will show that R is convex valued. Yeah.
How does Yi being convex not translate to their product?
It follows trivially actually that if A and B, this is a standard property, that if A and B are convex, or they are A and B are convex or closed or bounded, the product will also have inherit that property trivially actually. So, I'll just quickly write the proof here. So, take any two sets A comma B are convex, and take now you take a point x and take 2 points x1, x2 in A cross B. This one, let us write this as x11, x12, and this guy, let us write it as x21, x22. So, now if you take a convex combination of x1 and x2, so you take alpha times x1 plus 1 minus alpha times x2, where alpha is in 0, 1. Okay. So, this is therefore now alpha times the first, you get a convex combination of the first component. So, this here would reduce to alpha x11 plus 1 minus alpha x21 and alpha x12 plus 1 minus alpha x22. So, this is in A, the lower one is in B. The A is because A is convex and B is convex, and so therefore, the product is also in A cross B. No. So, the multilinearity would, so this is the set of all probability distributions. The set of all probability distributions is convex. If you constrain the set of probability distributions like through a Markov chain or something, then then it is not necessarily convex. Okay. Alright. So, now we want to show that R is convex valued. So, for this, let us recall, go back and see what R was. So, R was the product of Ri's, and each Ri is the set of best responses of player I. Okay. So, Ri of y minus I is the set of best responses of player I to y minus I. Okay. Now, this what we want to, so it is to show that R is convex valued, what we will show is that each Ri is convex. Okay. Each Ri is convex valued. In other words, if you fix a y, then for every I and Ri of y minus I is going to be a convex set. Okay. Now, why is this a convex set? Means why is the set of best responses always a convex set? Okay. So, for that we need to just carefully look at what is actually happening here. Okay. So, and this is, once we understand this, the next part will also follow very easily. So, if you look at the cost of player I, that is listed here, that is written here, it is this expectation, right. Now, what we are doing is, when we are evaluating the best response, what we are basically asking is, we are fixing all the y minus i's. Okay. So, we are fixing the mixed strategy of the other player and asking what is the best that this guy can do. So, if I fix everything other than yi here, so fix all the yj's other than yi, then what sort of expression is this in yi? It is linear in yi, right. So, if you look at this expression if you see it's as a function of y1 to yn, it is actually, it has this product of all the y's involved. Okay. So, it will in fact be a polynomial in y1 to yn, right, because it will be a polynomial, each term involving a product of n monomials, right. Okay. So, this is going to be a polynomial, but if I fix the y minus I, then it is linear in yi. Clear? So, which means that what are these best responses? The best responses are actually solutions of a linear program. They are the ones that minimize this linear function over all the y, right. So, in other words, this here, so now let me go back here, Ri of y minus I is simply the solution set of this linear program, right. It is argmin of Gi of this over yi in capital Y. Okay. And this here, this chap here, this guy is linear in Y. Okay. Now, if this is linear, the objective is linear in y, what about the constraints, which is this capital yi? Capital yi itself is defined by two linear constraints. It is defined by the requirement that 1 transpose yi is equal to 1 and yi is greater than equal to 0, right. So, if you put together this these two facts, the objective is linear in yi, the constraints are also linear in yi, which means then that Ri of y minus I is simply a solutions, is the solution set of a linear program or a linear optimization problem. Now, if this is the solution set of a linear program, then what does this, what do we know about the solution set of a linear program? We know that the solution set is always going to be, if there are two solutions to a linear program, then every segment, the entire line segment joining them is also going to be a solution, right. Which means that if you have 2 points in Ri of y minus I, then the entire line segment joining them is also in Ri of y minus I, right. Which means what? Which means that if you have 2 points in Ri of y minus I, the convex, every convex combination of those 2 points is going to be in Ri of y minus I, which means Ri of y minus I is actually convex, right. So, if you take 2 points in it, the entire segment joining it is also in that set, which by definition makes the set convex, okay. So, which means that the Ri of y minus I is actually a convex set. Is convex, and it is convex for each value of y minus I, for each y minus I. So, you fix y minus I, you get a convex set. So, what does this mean then? Therefore, then R itself, R of y was itself R1 of y minus 1 till Rn of y minus n, and each of these guys is a convex set. Each of these factors in this product is a convex set. So, therefore, this R of y is also a convex set. And this is exactly what we wanted to show. We wanted to show that R is convex valued, right, which means that for every y, R of y is a convex set, means that R is convex valued. Okay, so let's go back to Kakutani again and let's see what he has to say. So, we have now knocked off this. We have shown that R satisfies this, okay, that it is convex valued.